Good afternoon, everybody. Welcome to lecture. Good to see you. We're going to start off with the survey question today. Rather than show it on the screen, I'm just going to draw it on the board so I can go through some transition state stuff with you. So the question gave you two molecules and asked you to predict the product and gave you a bunch of options to select from for answers. And this is a Diels-Alder reaction because it contains a diene piece. And it contains a dienophile piece. And what I'd suggest is that you line them up in a transition state, six-membered ring transition state like we talked about. So if you take the diene, first thing you need to do is rotate it to put it in an S-cis conformation. And I'll draw that over here looking like this. Now, it's just important when you do this that you don't make any mistakes about where the substituents are located. So this is a 1, 2, 3, 4 carbon diene, and it's got methyl groups on the 2 and 3 positions. So just make sure that you've got the same structure over here, that it's the same molecule, just in the different conformation. Okay, then you got the dienophile here, and this is the dienophile part, the part that reacts to make the new bonds, this carbon-carbon double bond. So we need to line that up. And this is one option. You could line it up like this, where you've got the double bond positioned this way. I could have also flipped it so that the ester and the methyl group were up top, but it's the same orientation. I'm just going to draw this a little bit better here. And the important thing here is that the ester group and the methyl group are on the same carbon. So that is something you have to turn up in the product. So the other thing I should say is this is not a trans dienophile. It's true that the ester and the methyl are on opposite sides of this double bond, but they're not on different carbons. So it wouldn't be appropriate to call this a trans dienophile. It's neither cis nor trans. It doesn't have stereochemistry. That's the thing. It doesn't, there's no difference between if you put the methyl here and the ester here, or the ester here and the methyl down here. It's the same molecule. So, and I think that was the complicated thing about this one, and it was the reason that I put it in as a survey question so you could see an example of a molecule like this. So let's just push the arrows around and get the product and then talk about it. So I'm going to start an arrow at the pi bond of the dienophile, and you can start it anywhere else you want. I'm going to push the arrows around counterclockwise. You can push them around clockwise. None of that matters. The important thing is that you use the arrows to predict where the new bonds are going to be, and you get the right connectivity. And in this case, this is the molecule. And there is stereochemistry associated with this molecule because there is a stereogenic center here. And so there's two outcomes. You could either have the methyl group be on a wedge and the ester group be on a dash bond, or you could end up with the stereoisomer of that, which looks very similar. It's just got the opposite orientation in terms of dashes and wedges. So it would have the methyl group on a dash bond and the ester on a wedge bond. But one of the things that I noticed is first of all, this wasn't the most popular answer, but it was the second most popular answer. The most popular answer showed the ester and the methyl on opposite carbons and having a trans relationship, which wasn't the right connectivity. Since that carbon in the dienophile has methyl and ester, then that has to follow all the way through. So that carbon right there has got methyl and ester. That carbon in there has methyl and ester. So, so that's the correct answer. And I think it's easier to see if you draw out the transition state. So check that out. If you got it wrong, just double check. Make sure you're comfortable with predicting products using Diels-Alder transition state. Any questions about this one, the survey question? All right, good. Okay, so let's talk about more about transition states, let's talk about exo and endo some more, because there's a little bit more that we have to do with this. And I want to kind of finish this up in a kind of good way before we move on and start talking about something different. So I'm going to talk to you about these transition state options again. So here is the general form of a transition state for a Diels-Alder reaction that's got exo and endo stereochemistry possibilities. So here's the diene part, and I'm going to draw it like this, where I'm pre-puckering the bridging group up, and then I'm going to draw the double bond of the dienephile down here. All right, now there are groups on this dienephile, and depending on the positions they're in, you're going to get one type of stereochemistry or another. So let me just point out that the carbons at the ends of the diene and the carbons at the ends of the dienephile are going to react to give the product to make the new sigma bonds. And then the groups that come with the dienephile, they are oriented like this. And the ones that are underneath the diene, these are called endo substituents. So this is an example of a position, an endo position. So if you have a substituent that's attached to the double bond and it's underneath the diene during the Diels-Alder reaction, that's an endo position. It's going to be an endo group. This is the other endo position. That one is underneath. And then the ones that are on the outside, the ones that are far away from the diene, those are exo positions. So this is a generic transition state that you could use for any of these reactions where you've got exo and endo stereochemistry possibilities. And then when the reaction happens, you get a product out where you can see the locations of all those substituents. The ones that were underneath the double bond, these are the endo positions. They're going to end up pointing down. So there's an endo spot. Here's another endo spot. And the ones that were outside of the envelope of the diene, those are going to be in exo positions. So this is going to be an exo spot right here, and then exo right there. So one of the questions that you'll be asked, and there's a double bond there as well, that you'll see if you look at old exams and things, is like, when you see a product like this, can you recognize which positions are endo and which positions are exo? So the ones that are pointing in opposite directions relative to the bridging group, which is there, these are endo. And the ones that are pointing in the same direction as the bridging group, they're exo. But the reason that they are the way they are is their orientation during the transition state. The exo ones are outside of the carbon-carbon double bond, and the endo ones are underneath. So the endo groups like to be underneath when they have pi bonds that can interact with the pi bonds of the diene. So that was one of the things that I drew when I talked about the transition state in that endo product, where there was this thing called secondary orbital overlap, where we had bonds forming where I'm showing the dotted lines here, but then we also had some overlap between the diene and the groups that were in the endo positions, because they had pi bonds on them. They had a carbonyl group on it, for example. So that's the kind of thing that you want to look for. Whenever you have a dienephile that has those pi bonds, that has a carbonyl or C triple bond N, or any kind of pi bond where it's got p orbitals that can overlap and interact with the diene, those substituents are more favorable to be in the endo position, which is why endo products are so popular. So one of the things I want to do now is go through and talk about the transition state for exo, because we didn't get a chance to talk about that last time. And I just want to put that up here and explain why it isn't as good as endo. What's wrong with exo? We said that endo was the most popular transition state, the one where the molecule favored that one when the substituent had like pi bonds on the dienephile piece. So here's a transition state for an exo product. And I'm going to use the same example that we used last time. I'm going to use an aldehyde that has this orientation. It's just got the carbon-carbon double bond that's part of the dienephile And then the dienophile has an C double bond O substituent. And those dotted lines, that's where the sigma bonds are going to form. And so you could imagine the way that these electrons would move is if you start an arrow at one of the pi bonds and you push this way, and you start another arrow and you push that way, and you start another arrow, you push that way, you get to a product. And the product is going to look like this. This is the exo product. So this substituent right here is in an exo position because it was outside of the, another double bond there, so it was outside the envelope of the diene during the reaction transition state. So it's not underneath, it's not in this position, it's over there. This H over here, which I'll draw right here, that H is underneath at this point. So that's an endo. That H is actually in an endo position, and here the carbonyl is exo. So why is this transition state not as good as endo? I'm going to erase these arrows, and I'm going to instead draw p orbitals to indicate where the pi bonds are. So the dienophile has p orbitals and pi bonds on all of its substituents here. It's got carbon-carbon double bond, p orbitals, carbon-oxygen double bond, p orbitals, and there's overlap here, and that's how the double bond is a double bond, why it's a double bond. And then the diene has these orbitals as well. And the orbital overlap that's going to produce sigma bonds here is that overlap. And that's the formation of the new sigma bonds in this product over here. That overlap is what's going to help that bond form. But the thing that is missing from this transition state that we had in the last one is that the p orbitals on the other part of the diene and the p orbitals on the substituent are nowhere near each other. They're far away, so they can't interact. So this transition state is not held together as strongly as endo. So this one is less favorable. So this is an exo transition state. And I'm going to say it is less stable than endo. So it ends up being the minor transition state, and this is going to be an exo product which is going to be a minor product. Okay, so exo and endo. Let's look at some examples where we try to figure out what's going on exo and endo with some different kinds of dienophiles, because I want to go over this. Is there a question?
Yeah, why can't the endo product occur?
Oh, the endo product certainly can occur, and so maybe what I should do is just briefly go over that one more time, because I want to make sure that we don't get lost with this. Let me draw the transition state for endo, and then you'll have them side by side and you can look at them. So endo is actually the preferred transition state. And if I draw that over here, this is going to look like this, where we've got the diene. The dienophile is going to be positioned underneath, though, this time. So in this case, we've got p orbitals on the diene that can interact better with the p orbitals on the dienophile. There's this interaction right here, which is leading to the sigma bond formation, which is the same kind of interaction you get over there. But here, the difference here is that the substituent on the dienophile that carries the p orbitals and the pi bonds, they can actually interact. So what this transition state has going for it over that one is that there's this secondary orbital overlap. So this is endo transition state. And the reason we're saying that is because the substituent on the dienophile is underneath. It's in the endo position, the one that's really important, the one that has the carbonyl on it. And this one is more stable than exo, because the exo didn't have this secondary orbital overlap that I'm indicating with the dotted line here. So this, this species is just held together a lot more tightly. There's more points of attachment. So this is the one that's going to dominate in terms of being the most popular transition state, and it leads to a product where that group that was endo ends up in this endo position in the product. So here, the carbonyl is pointing down in the opposite direction of the bridging group. All right, so two different transition states. This one is better because it's more stable. All right, I want to give you a question that'll make you think a little bit about exo and endo. All right, here is a diene, the same one we've been looking at, and then here's a dienophile. What product would you get out of this? And what I'm going to do is I'm going to draw the skeleton of the product, and then we're going to arrange the substituents from the dienophile and put them in the appropriate spots. So this is a good skill to be able to do. It requires that you understand about exo and endo and what this picture means. Okay. So what I want to do is to put groups here, 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 and here to represent what you would get from this reaction. Okay, so first of all, the substituents on this dienophile, the carboxylic acid here and here, they have p orbitals. They have it's a pi bond there. So these would be happy in an endo position. So can I just draw the product where they're both in endo positions, do you think? I'm hearing some no's. Why not? Endo is better, isn't it? I mean, what's the problem with that? I see trans is what I'm, yeah, it doesn't, this molecule doesn't support that. You can't get both of them underneath because this is a trans dienophile. So no matter what, only one of them can be in an endo position. The other one's got to be in an exo position. So you could draw the product either with the carbonyl group on this spot being in endo, but then the exo position is where the other one has to be. So in other words, it's still got to maintain the cis-trans nature that the dienophile came in with. That stereochemistry has to be retained in the product. This is a trans product. If you put both of these groups in endo positions, that one's only possible from a cis dienophile. So in other words, the rule, Diels-Alder rules still apply here. You still have to maintain the stereochemistry of the dienophile in the product. Okay, so that's an important kind of deal. If you had a cis version of this dienophile, if the carboxylic acids were both on the same side of the line, then the one where they're both in endo positions, that'd be the best one. So let's maybe take a look at that example. Just because I want to make sure that it's understandable in a picture form rather than just in words. So if you saw this Diels-Alder reaction and just for consistency, I'm going to use OH groups. On the carbonyls, I'm going to use carboxylic acids as my substituents. When this reacts, you're going to get a product that's got endo positions, which I'm drawing there, and exo positions, which I'm drawing there. And the idea is you just have to get the right substituents in the right spots. These can both be underneath the diene in the transition state, and they would want to be, and that's the endo position, because they have these p orbitals that can overlap with the diene and help stabilize the endo transition state. So this is one that this would be the product. I mean, this would be the major product. And then the H's would be in these exo positions. So yeah, it's like a regular Diels-Alder reaction, these ones that have these exo and endo features. It's just that there's this bridging group that we have to worry about. So any questions about exo and endo? Diels-Alder reactions in general? There's one more Diels-Alder concept that I want to go over before we move on, and that's how you think backwards about Diels-Alder reactions, because there's some really good questions in the homework and on old exams that deal with this. So in other words, it's like, if you had a cyclohexane that you were given, how could you plan a Diels-Alder reaction that would make it? So to illustrate that, I'm going to draw a cyclohexane product. I'm going to make it look like this, and I'm going to say what would be your diene? And there might be a box there that you have to fill in. And what would be your dienophile? And I'll put a box here. So you might have to predict what starting materials would I use to get a Diels-Alder reaction to produce that molecule right there. This is a little different than predicting the products of a Diels-Alder reaction. This is predicting the reactants of a Diels-Alder reaction, which is kind of a different skill, a little bit different skill set. So there's different ways to approach this. One way you can approach it is if you recognize that you find the cyclohexane in the molecule that came from the Diels-Alder reaction. It's right here. And if you understand that it's these bonds that were made in the Diels-Alder reaction, that those sigma bonds are new and that pi bond is new, that basically then that's how it came together. That line represents the point where the two groups attached. The stuff on the left came from the diene, and the stuff on the right came from the dienophile. So you just have to pull them apart, make this into a diene, and if you wanted to do that, if you're able to, you could just imagine, for example, doing this, where you put the double bond here, single bond, double bond, that reproduces the diene that it would have come from. And then the dienophile part is basically all the atoms are there. It's just that you've got a double bond now where there's a single bond. There used to be a double bond there. So those are the two pieces. So that's one approach to it. If you like that approach, go ahead and use it. There's another trick you can use if it's helpful. Some people do find it helpful. And that's to write arrows to predict the Diels-Alder reaction in reverse. Here is an example of that. So I'm going to draw the same structure over here as I have in the previous board, but I'm going to show you a different approach to predicting the starting materials, and that's one using arrows, curved arrows, to undo the Diels-Alder reaction. So this is what would happen if the Diels-Alder reaction went backwards? That's called a retro Diels-Alder reaction, and these are possible. And the way to predict that is to start an arrow at the pi bond that's left and push it either clockwise or counterclockwise, doesn't matter which. And with this arrow, I'm saying take that pi bond and make a new carbon-carbon double bond here. Well, if you do that, you got to break a bond to this carbon because it already has 4 bonds. So you can break this bond and push it over there, saying make a new carbon-carbon double bond here. And then if you do that, you have to break this bond and slide it over here. So it's essentially just the reverse of what we did to get the Diels-Alder product in the first place. And if you follow those arrows then, what it leaves you with is the product where you've got the carbon-carbon double bonds on the diene in the correct spot, and then the carbon-carbon double bonds of the dienophile where they belong. And the substituents as well, and it even gives you got to make sure you get the stereochemistry right. Since this was a cis Diels-Alder product, the 2 groups were cis that were part of the dienophile. You got to show the dienophile as being a cis dienophile. But that's another way to do it. And if you're not sure you have it right or not, you could imagine going backwards and doing a Diels-Alder reaction with it. If you push these arrows around in a circle, you should get that. So a couple of different strategies. Practice whichever works well for you. But those are going to be questions that you'll see frequently. These predict the reactants to make the following Diels-Alder product. Sometimes you'll need to provide a missing diene. Sometimes you'll need to provide a missing dienophile. Sometimes you'll need to produce both, supply both. So just depending on the nature of the question. All right, so that's the end of the chapter. Do you have any questions about it? Like lingering Diels-Alder things? Okay, we'll give the homework a try if you haven't already, and just if you have any questions, let me know. And now we're going to move on and talk about something different, but still where conjugation is a really important component of it. The way that the textbook chapters are laid out is there's a bit of a theme to them. And conjugation is a big important part of this next chapter that we're going to be dealing with, which has got to do with benzene and aromaticity. So this is the next thing we're going to tackle. So this is chapter 15. And it's about benzene and aromatic compounds. It's really about trying to understand what's special about benzene, because benzene is an important molecule. If you haven't already realized that or picked up on that, just open any textbook that's got chemistry in it and structures, and you'll see this like everywhere, almost every page. It's a super common substructure that you see over and over again in organic chemistry and biochemistry, just everywhere. And the reason is it's a really stable arrangement of carbon atoms and hydrogens. So, so why is it so stable? We're going to tackle that in this chapter. Let's talk about a little bit about its structure. First of all, this is one resonance structure of it, and you can draw the other one by pushing electrons around in a circle like that to arrange them differently, to share them differently, and that gives this other resonance structure. So these are what are called Kekule structures. They're resonance structures of each other, and they were first proposed by a chemist named August Kekule, published a paper on it, and at that time nobody really knew exactly what benzene's structure was. They knew it had formula C6H6, but they didn't know how the atoms were connected, and proposing this alternating series of double bonds, single bonds was really pretty revolutionary. And so we still call them that. But these are just resonance structures. But the point is it isn't like this or like that. It doesn't switch between the two. It's like both of them at the same time. So a resonance hybrid for this, what it really looks like is benzene, a 6-membered ring, but with kind of a bond and a half between each one of the between the carbons of the ring. And so sometimes people will emphasize this by drawing benzene like this, where they just draw a hexagon with a circle in it. So you may have seen that representation in other contexts, other textbooks or online or something like that. That's a real common representation. And what it's doing, what all these pictures are doing, is emphasizing that benzene's got 3 pi bonds in it, and there are 6 pi electrons in this structure. In this picture, there's overlapping p orbitals, and the p orbital, the pi bond is 2 electrons in that shared overlapping space between the p orbitals. Same thing here. There's 2 pi electrons here, and there's 2 pi electrons there. So you add them up and you get 6. This structure just shows the electrons shifted by 1 bond. And in reality, what you have is 6 pi electrons that are equally shared over all 6 atoms. And that's what this picture is trying to represent, and this picture also. We know that this is the way it is because if you measure the bond lengths in benzene, and we can do that using a technique called X-ray crystallography, where you grow a crystal of benzene and you shine X-rays on it, you get a diffraction pattern, and then you can see, based on that diffraction pattern, decode where the electrons were. That all of the bonds, the carbon-carbon bonds in benzene, are all exactly the same length. They are all C-C bonds are 1.39 angstroms. And angstroms is a measure, unit of measure. It's 1 × 10⁻⁻10 meters. It's like related, it's close to nanometers, but not quite. And just to give you a little bit of reference, if you were to look at a pure carbon-carbon single bond like you get in ethane, that bond length is 1.53, I believe. I'm going to have to double check on that. Yep, 1.53 angstroms. So it's longer. And then if you were to look at the carbon-carbon double bond length in a molecule that has 1 full double bond, it's shorter. It's 1.34 angstroms. So what this is saying is that this is like somewhere halfway between these two. It's not, the bonds aren't full single bonds and they're not full double bonds. They're partial bonds, a bond and a half about. And they're all the same. It's a perfect hexagon. So that is benzene's structure. If you look at an orbital picture of benzene, I'm going to draw this. This is a structure I've drawn before, but I'm going to do it again. So the overlapping p orbitals on the upper face form one of the 2 donuts, and the overlapping p orbital lobes on the bottom face form another donut. In the middle is the carbon atom ring. So that's a picture of benzene, and there's a total of 6 electrons that are occupying this overlapping space. So I'm going to tell you 6 pi electrons are located in the overlapping p orbitals. I'll also call that a pi system. So the pi system here is the donuts, basically. The overlapping p orbitals form a region that electrons can move around in and can exist in and occupy space in. And there's 6 of them occupying these donuts. So that's the core structure of benzene that is really central to why it behaves the way it does. The other thing about benzene is it's got an unusual stability about it. And we're going to come back to this concept because it's really important for understanding why it's all over the place, is because it has an unusual stability. We're going to look at that later. But the next thing in the chapter is to talk about naming. So we're going to just discuss a little bit about how do you name benzene rings. So this is about classification of benzene and its neighbors. So, or its substituents. So naming benzene. Maybe I'll say is benzenes, because substituted benzenes are what you really have to name. So there's a bunch of different rules. When the group attached to the ring is alkyl or a halogen, just name it as a substituted benzene. For example, here's benzene with an ethyl group on it. You just call this thing ethylbenzene. Ethyl, and then you don't go, no space, just go right into benzene, ethylbenzene. And then here's a benzene ring that has a chlorine on it. That's a chloro group. This would just be called chlorobenzene. Okay, so a lot of times it's really simple like that. What has happened over the years, though, is that there are certain special names that have evolved. Because benzene is such an important molecule, it's been known for such a long time, people have been dealing with its derivatives for a long, long time, and they've got names. Some of them have special names. We're going to learn about these special names. They're sometimes called parent names or root names. So I'm going to say some benzenes have special parent or root names. And we're going to look at a few. So the ones we're going to deal with, I'm going to put on the board right now. If your benzene ring has a methyl group on it, it would be totally illogical to call it methylbenzene. The thing is it's evolved to have a special name, and it's called toluene. So most people would not call this methylbenzene. They would refer to it as toluene. And the name implies that it's got a methyl group on the benzene ring. Another one that's really important is benzene ring with an OH group on it. This one is called phenol. And a lot of times the reason that they have the names they do is historical. In other words, they've been known for like hundreds of years. So they just got the name, and probably long before people even knew what the structure was. When your benzene ring has an NH2 group on it, it's called aniline. when it has an OCH3 on it, it's called anisole. And then the last two are a little bit easier to remember, I think. They kind of, there's hints in the name as to what the functional group is. This is called benzaldehyde. So you could like figure that it has an aldehyde in it if it ends in the word aldehyde. So benzaldehyde is a benzene that has an aldehyde group on it. And the last one that we're going to look at is one that has a carboxylic acid on it. So if you have a benzene ring that has carboxylic acid as a group, this is called benzoic acid. And the thing about this one is there actually is a space. Most of the time with nomenclature, you leave the spaces out, but once in a while, there is a space. These are technically two separate words. It's benzoic acid. So if you're doing naming in ALEX, leave the space out or it'll probably flag it as wrong. And then you might be confused. So these are root names, or parent names. If you ever see this in a compound, you want to try to use the root name to help you name it. We'll see examples of that in a little bit. The next thing we need to talk about is how do you name substituents when there's two of them on a ring? How do you indicate where the substituents are? Because when you have a benzene ring with two things on it, there are different ways to do that. There's three different ways to do that, and we're going to look at those examples now. So this is a discussion of naming disubstituted benzenes. And the example that I'm going to use is benzene that has two chlorine groups on it. So if you have a benzene ring and you have two chlorine groups on it, one option is that the chlorines are right next to each other on the ring. There are two ways to indicate the location of these chlorines. You can either call it ortho. So ortho is the new term. Orthodichlorobenzene. The ortho is usually written in italics, which is why I underline it. When you're doing it on an exam or an ALEX, I don't think you need to be that particular about it. Sometimes the ortho is abbreviated with a little o. So if you see a little o and it's italicized, O dichlorobenzene is referring to the fact that it's got this ortho relationship. The chlorines are next to each other. That's what ortho is going to mean. We're going to need to remember that. But sometimes it's just abbreviated with a little o. And then the other way you can talk about it is just to give them numbers. So if you numbered the ring and started at one of them, 1, 2, 3, 4, 5, and 6, the chlorines are with a 1-2 relationship to each other. So another way to do it would be to call it 1,2-dichlorobenzene. Just another option. Okay, what happens if your chlorines are not next to each other but are a little bit further apart? It's a different name. So if your chlorines are having this relationship where they're not right next to each other but they're not exactly opposite either, this relationship is called meta. This would be meta-dichlorobenzene. Or little m dichlorobenzene would mean the same thing. Or if you were wanting to number it, you might see a numbered variation on this where it would be 1,3 dichlorobenzene. And all of these systems are used interchangeably. You'll see them mixed in. There isn't one that's like really much more popular than the other. Systematic nomenclature really likes the numbered versions of these things, but you could, the meta, orthometa, and we're going to see para, that's a usage that's very common. So you got to be able to recognize it. Okay, so I don't have any room over here, so I'm going to move over to the next board and talk about the arrangement, the third possible rearrangement of substituents where the chlorines are exactly opposite each other on the ring. So the third and final way to arrange two groups on a benzene ring is to put them on opposite sides. And this arrangement is called para. So this would be para-dichlorobenzene in one naming scheme. You might also see with a little p. The p, by the way, should be a lowercase p. It's not a capital one. P. Dichlorobenzene, which is just an abbreviation for para. Or giving the substituents numbers is another possibility. So you might see this as 1,4-dichlorobenzene. So there's some nomenclature about naming disubstituted benzenes. When you have a benzene ring that has multiple different substituents on it, you want to try to use the root names whenever you can, because it'll make the name easier. Use root names whenever possible. So for example, if you were to see this molecule, what you'd want to do is look to see if you can identify one of the root name arrangements that we saw. And if you study this, and it's going to take you a while to get used to some of these root names, but if you look long enough, you'll see it's got that in it. That's a phenol. So one way to name this thing would be to call it ortho ethyl phenol. That'd be one way to do it. You could do a little lowercase o ethyl phenol. If you want to number it, you can, but you should give the root name the number 1 spot. So the root group defines position number 1. So that's helpful. If you wanted to give this a numbered name, you'd call that position 1, and then you'd want a number around the ring to give the lowest possible number to the group, and so it would be in the 2 position. So another way to call this would be 2-ethyl phenol. And notice I didn't say 1-phenol because the root group is defined to be at the 1 position. So you don't need to include that 1. It's just everybody knows 1 is where the OH group is because it's a phenol. Okay. Let's talk about some other situations. Maybe we'll go through like a system of things to do, like a hierarchy of rules to apply. And then we'll go through some examples to test those. And in case you're wondering, and this question usually does come up once in a while, I'm not going to give you examples where there are two root groups in one molecule. In other words, I mean, these molecules really do exist, and there's a set of rules that tells you which root name is more important, but to me that's mostly memorization and I don't want to focus on it. So all the examples you are going to see just are going to have one root group or none. So if you find one of those root groups, then use it, identify it, and define the number one position with it. And then the next thing you need to do is number around the ring to give the lowest set of numbers. Then what you're going to want to do is alphabetize the substituents. And include these in front of the root name. So let's go through an example or two to work on this. All right, I've got a benzene ring here that has an ethyl, a chloro, and a bromo. There are no root names that can be ascribed to this molecule. None of these groups are among those that we listed as being special. So what you'd name this thing as is just then as a benzene. So that's the name, it's a benzene. It's a substituted benzene. So we need to number around the ring to give the lowest numbers to the group. So just start one place and see what strategy you can come up with to give low numbers. And it turns out if you start here, give that a 1, and that a 2, and then 3 and 4, you get the lowest possible numberings. If you were to try to do it any other way, you'd end up with some higher set of numbers. So we have an ethyl group in the 1 position, a chloro in the 2 position, and a bromo in the 4 position. So then you alphabetize these groups. B for bromo is going to be first, and then C for chloro is going to be next, and then E for ethyl is going to be last. But we're going to give them the numbers based on what I've got up here. So the name of this molecule would be 4-bromo. Two chloro, 1 ethyl, and then no space, just go right into the name of the molecule, benzene. 4-bromo, 2-chloro, 1-ethyl benzene. Okay, let's take a look at another one. This one has an ethyl in that same spot. There's one of these, and then there's one of these. So here's one where you have to recognize the root substituent is a phenol. So I'm just going to lasso that out to highlight that. And then that defines the number 1 position. So when you have a root group, it's kind of nice because you don't have to worry about where 1 is. You know. Your job then, though, is to find the best way to number around the ring to give low numbers to the groups. And if you number around counterclockwise here, this would get a 2, we get a 3, a 4, and a 5. So we'd have a 2-5 set of substituents. That's better than going the other way, because if you went the other way, you'd have a 3-6 set of numbers. So that's the best way to do it here. And so then you alphabetize again. C for chloro comes before E for ethyl. So the chloro substituent would be first. That'd be 5-chloro. And then in this case, 2-ethyl phenol. And like you saw before, you don't specify the position of the root group because you know it's the 1 position. So that is a good intro to naming. We'll do a little bit more with it next time. We'll start talking about benzene's unusual stability. So have a good rest of your day.